Good evening, guys. So, as usual, we'll start with our revision session first, and then we'll follow it with the solution for the assignments. And I hope you all have completed your week 5 lectures. I think most of you have might have started the week 6 as well. So let's start with the revision. And meanwhile, if you have any doubts, please feel free to interrupt in between. Okay, so in week 5, uh, we have the goal of week 5 was to understand the design problems for sizing of PV applications. Like if we are supposed to if we are given a problem statement that we have to design PV for a given area, be it a rooftop or a solar field, whatever kind of application it is, how will you size your PV applications? So in general, any PV applications we have seen can be divided into two parts, or it could be two alternatives. One could be we could design PV system with storage, or another is we could design a PV system without storage. So these are the two options that are available to us. Okay. So when we talk about with storage, that means we could use there are different types of storage that we'll see in the coming slides. And when another option is without storage. So when we talk without storage, few of the examples of without storage are PV to grid. Like whenever PV is directly connected to the grid, then in that case, battery storage is not required. We can directly connect the PV output to a DC to DC converter, and that will be connected to or directly an inverter, or we could use a two-stage converter, that is DC to DC and then DC to AC. That way we could connect PV to grid. That is one of the examples. Another could be a solar operated water pumping system. So water pumping system that is operated with the solar input. So solar input will be given to a pump motor that would be used either for our irrigation purpose or in order to store the water in the overhead tank. Any kind of application can be it can be used for. Okay, and then a few other applications are cooling applications and heating applications. So these are few of the examples where PV system is designed without storage. So let us start with PV sizing without storage because it is much simpler to understand. So that is why we are starting with this, and then once after completing this, we'll just add storage also to this type of sizing procedure. Okay. So now, as you can see in this diagram, there is a house. We are considering just one house. This house is connected with solar PV. Now, what happens in our house is currently, if you don't have solar in your house, you can see the blue path. This blue path. You are just having this kind of connection. That means you are just drawing power from the grid. If the black lines are the grid lines, then you can see here that we are just drawing power. That means only the blue meter is operating, right? The blue meter. That means only blue meter is coming into picture when we are just drawing from the grid lines. But if suppose I have connected the solar panel in my roof, and now what will happen is my solar panel will be generating certain energy, and that energy will be again connected to some other kind of energy meter, that is the green energy meter, and we'll push that energy into the grid. So now I am not only just drawing the power from the grid, I am also pumping the power into the grid. That means in one direction, I am taking power from the grid, that is the blue area line, and in another part, I am pumping the power into the grid. That means if WH is the watt hours of the load that I am consuming, and WH is the watt hours of the PV that I am pumping into the grid, then the net energy I am consuming, that is WH load minus WH PV, right? So this is the net energy that I am consuming. Now, there are two modes in which this net metering or this metering mechanism uh, can be taken care of. Is first mode is zero net energy transfer. Another one is zero net cost transfer. So you could have two aims for this kind of energy transfer. Either you could target net zero net energy transfer. Zero net energy transfer means the energy that I am consuming from the grid, that is WH load, should be equal to WH PV. that is the energy that I am pumping into the grid, right? If the energy that I am taking and the energy that I am giving back to the grid, if they both are equal, then I can say that I have achieved the condition for net zero energy transfer, right? Now, another kind of aim for this kind of topology could be zero net cost. Now, when will we achieve zero net cost? Let us see how we'll calculate the net cost. Suppose, see, now usually what happens is, since government is subsidizing solar, therefore the tariffs for solar is different from what our normal energy consumption is. Sometimes you are even paid higher if you are pumping solar energy into the grid. Okay, so let us assume that the tariff for my normal power is C load and the tariff for PV is CPV. Then if I multiply my watt hour load with the tariff and watt hour PV with its respective tariff and then subtract the both of them, that will give me the net cost. Now, another aim could be zeroing this net cost, right? So using these two, you cannot do both obviously simultaneously. Okay, but depending on what your target is with this topology, what kind of target you are trying to achieve, whether you are trying to achieve self-sufficiency or you are trying to zero the net cost. Depending on that, you can use any of these modes. You can operate in any of the two modes. You can start your design with that. Okay. And in our houses, we all know that our bill comes depending on the number of units of energy we have consumed, right? We all have heard of this term unit. Now, 1 unit is equals to 1 kWh. Okay. And our monthly bill comes in units per month, which is kilowatt hour per month. Okay. Now, for sizing, what we start with is we first of all determine the HAT minimum. Remember in previous classes, while we obtained the curve for HAT, we sort of we from the curve we obtained the minimum HAT from that curve. If this was our curve, like this something we got, right? And then this minimum level of energy watt hours we have calculated and we have called it as HAT minimum. Now, what is the significance of that HAT minimum? This HAT minimum is the minimum energy that is available on any kind of tilted flat plate collector considering atmospheric effects in 1 day in any of the year. That means throughout the year, this is the minimum energy that my flat plate is going to get. So if I am designing my system according to this minimum value, then my system will always be generating more than this, right? So when I am designing, I have to design for the worst case. That means if my solar panel is able to supply to my system even on the least energy day, when my solar panel is getting the least energy, then rest of the day I will always have surplus energy, right? That energy, surplus energy, I can always pump into the grid. So this is what we are trying to achieve here. So using HAT minimum, that is why we have started our calculations with HAT minimum. Our design should be capable of delivering the full load requirement even during the least insolation day. If we are able to meet this least insolation day requirement in this curve here, then if I am designing for this, then during rest of the months and rest of the days, definitely my solar will be generating surplus and it will be and my system will be self-sufficient. I won't need any other kind of power supply for my home or whatever application I'm designing this for. Okay. So now if I take a solar panel and assume that standard insolation is falling on the panel, that is 1 kilowatt per meter square, and assuming the area of the panel to be A, then if the efficiency of my system is eta, then the output power is efficiency into input power, right? Since efficiency is output upon input, so output power can be written as efficiency into input power. Now, this input power is insolation into area, right? We have already seen this. This will give me the output power in kilowatts. Now, if I want energy output, then I will have to multiply it with the equivalent hours. We have already seen that using HAT minimum, we can calculate the equivalent hours. And the significance of equivalent hours was if I am having standard insolation on my solar panel, that is 1 kilowatt per meter square, then for how long, for how many hours will my panel supply the energy? will the solar panel be generating. So that is the significance of our equivalent hours. We already know how to calculate these, right? So we'll just multiply it with these equivalent hours and we'll get kilowatt hours. This is the energy output. We can call it as WHPV, watt hour PV. So this is efficiency into area into HAT minimum. And in this, always remember these units. Since this is in kilowatt, okay, this might cause you problems in numericals. So this area that you obtain here is we call this area as intrinsic area. Now, why do we have to use a separate term for this is because you can see in this image that is present in this is a solar field, big solar field, okay? You can see that they have left spaces in between. Yeah. So this space you can see, right? The red marker space, this all space. So since it is like it is a top view, that is why you are not able to see the space in between, but space is there everywhere. Okay, so you can see here large amount of space is present. Okay, that means if I calculate certain area A, that is what we called as intrinsic area here. This area will not be exactly equal to the area of the field or the estate that I am going to buy or the area of rooftop that I have. So the area of rooftop that I have is EAS estate. This is what I already have. Now my panel will have to be put at certain space between them because I will have to do the cleaning of these panels. I will have to do the maintenance of these panels, installation of these panels. So in order to do all these things, I need extra space. So in order to take care of that extra space, we add 30% more area and call it a estate. So the area that we obtain from this equation is the intrinsic area, and then later on we increase this area by 30% in order to take into account for the estate area. Okay, so estate area is the one that I am going to actually ask for. Suppose I have my A intrinsic comes out to be 1 acre. Okay, for a big solar field, then I will demand for 1.3 acres of land, not 1 acre of land. That is the significance of this parameter. Okay, now let us move on to PV sizing with storage. First of all, why do we need storage? So the reason we need storage is because we know that the input to the solar panel comes from sunlight, and sunlight is continuously fluctuating from every minute. One time it will be shady, one time it will be very sunny, so it keeps on fluctuating. Since our solar input is fluctuating, its output also is fluctuating to an extent. Even after applying certain algorithms, its output is not always constant. Therefore, in order to and if my load that is connected to the solar output is sensitive kind of load, that is, it needs constant electrical input. Then what I'll have to do is I'll have to connect a storage buffer in between. That storage buffer could be of multiple types. We'll see later on there are multiple types of energy buffers that I could have placed here instead of just a battery or a charger system. But for now, for our particular, since electrical energy is one of the most high grade energy, that is why for now we are considering electrical energy here, and this energy storage is provided using this charger here. So we need, so this whole system will have our PV panel, we'll have energy storage, then we'll have a power converter in order to convert the DC that is available into the kind of supply that my load needs. Okay, so therefore power converter will be need. Now suppose if I am considering electrical kind of energy storage, then that will contain battery, that is a chemical device that could convert chemical energy into electrical energy, and then there will be a charger system. Basically it will be a power electronic converter that will help me charge and discharge both ways. And then the rest of the circuit will be same. There will be a power converter, there will be a load. Okay, so this battery charger system acts as an energy buffer. So this is the case that we are considering for now for our calculations purpose. Now, let us go in depth on the topic of batteries. There are two types of batteries, primary and secondary. Now, the difference between primary and secondary is the one that can be discharged only once are called the primary ones. That is the AA batteries that we put in our remotes. We just use them Whenever they're discharged, we just throw them away, right? We have got the chargeable types also in that, but they are of different chemistry. So the ones that we can use only once are called the primary cells, and the ones that we can charge and discharge again and again, they are called secondary cells. So few of the examples of primary cells are zinc manganese oxide, zinc silver oxide, etc. And few of the examples of secondary cells are lithium polymer, nickel metal hydride, lead acid batteries, lithium sulfur dioxide, etc. So these are the two kind of batteries. And since we know that in our PV application, we will be continuously charging, discharging, charging, discharging, there will be multiple cycles, right? So therefore, for our PV applications, without any thought, we have to go for a secondary kind of battery. Okay. Now, after selecting what type of battery you're using, primary or secondary, there are other parameters for the battery. So, in order to finalize the value of those parameters, we need to understand the meaning of these parameters. So, first parameter is the capacity of the battery. Now, the capacity of the battery can be calculated in two terms. First is the energy capacity, or it could be a charge capacity. Energy capacity is in watt hours, and charge capacity in ampere hours. Most popularly, we generally use charge capacity because our battery voltage is almost constant. Power is the product of voltage and current, right? And energy is integration of power. So now voltage and current out of both these parameters, since for our battery voltage is almost always constant, therefore charge capacity is equivalent to energy capacity. Both can be interchangeably used for our batteries. Therefore, more popularly, we you might have heard whenever you go to buy a battery, they will ask how many ampere hour battery you need, what all these parameters. So this is one of the first rating that you talk about when you talk about a battery, electrical battery. Okay, so we will focus on charge capacitor for our application right now. Now, below is a diagram of a battery, and it's a 12-volt battery. So if you see, the battery has two terminals, positive and negative here, and this is the full charge level of the battery, and this is the zero charge level. Okay, now let me assume that I have charged this battery to X level. Then for this X level, the amount of charge that I have stored in the battery tells the state of charge of the battery, and the remaining amount is called as depth of discharge. Okay, so they are both sort of complementary. 100 minus state of charge will give me depth of discharge, and vice versa. Okay, and there is always, for all the types of batteries, depending on what chemistry battery I am using, there is always a minimum depth to which battery can discharge. So this from top to this minimum depth, this is the usable watt hour or the ampere hour of a battery. So with this diagram, always keep this diagram in mind. So you'll be when you keep this diagram in mind, you will be able to understand the significance of all these parameters, right? Then minimum depth, when you are given the minimum depth, then you know how much of ampere hour capacity is the actual usable. Suppose I have a 100 ampere hour battery, but complete 100 ampere hour will not be usable in practical conditions. I will be able to use only a percentage of it, say 80 amperes hour. Rest of the 20 I will not be able to use. So therefore, usable capacity of my battery then will become as 100 ampere hour, right? So for this 12-volt battery, nominal most there is always a range of voltage. So the minimum is 10.8 volt and maximum is 14.3 volt. So does the 12-volt battery always remain at 12 volt? No, it keeps on fluctuating, but there is a fixed range. So there is a battery management system that we have in all the electric vehicles. There is there we don't we need very accurate amount of uh, battery characteristics. So in order to maintain those characteristics, we put a converter on the top of this battery in order to monitor our battery. So this battery management system has the job of checking whether the voltage range is within 10.8 volt to 14.3 volt. If it goes below 10.8 volt, it trips. It disconnects the battery basically. And if it is charged more than 14.3 volt, then again it disconnects the battery from the charger. So all these operations does not happen manually, or it does not happen using just the battery. There is a converter in between, and in all the electric vehicles, battery management system is one of the most important part. Now, another parameter after capacity is C rate of the battery. C rate of the battery is the rate at which battery is charged or discharged. So you cannot just charge any battery at with any charger, right? For our phones, all of us have different mobile phones which have different chargers, and we all have sort of heard that don't connect the even if they have the same connector, don't connect different connector to your phone. Otherwise, your battery will might get damaged or its life might get reduced. We all have heard of this notion. So the reason is that because there is a desired way or ideal way to charge any kind of battery. And this C rate is one of the most important parameter of that ideal way. So the rate at which I charge or discharge my battery is called C rate. Now, if the capacity of my battery is in ampere hours and I have n number of hours to discharge it, then the average battery current will be called as IB. IB will be the average battery current. There is a range of that IB. There is always a range of IB that your battery can take. You cannot charge or discharge any battery at any average battery current. There is a desired, feasible, or more practical range in which the efficiency of your battery is good. So your charger is designed to supply that average battery current, which is desirable for your particular battery. That is the reason you should use that particular charger for particular battery and not exchange those. So now there is a notation for this C rate. Sorry. So there is a notation for C rate. So if any number is written on the right hand side of the C, then you divide by that number. And if any number is written on the left hand side of the C, then you multiply by that number. For example, for C10, you will divide the capacity by 10 because it's written on the right hand side. So if the capacity of my battery is 20 amperes hour, then for a C10 battery, my rate would be 1/10 of the capacity. That means my average current will be 2 amperes. What will this mean? It will mean that a 20 ampere hour battery can supply 2 amperes average current to the load for up to 10 hours. But this is ideally. Practically, it will not go up to 10 hours. It will be somewhat less than 10 hours. So whenever you make practical calculations, always that is why you apply a factor of safety. So if I want my battery to work for 10 hours minimum, then I need to take a battery that will work for more than 10 hours. These are things that you need to keep in mind while designing a practical system. Now, if you look at the graph of the battery voltage with time, ideally what you will think is my battery should always have a constant voltage, right? We always thought so far that our 12-volt battery should always have a 12 volt. This is the ideal curve, 12 volt, 12 volt, 12 volt. And the moment all my charges, all my my complete battery is discharged, suddenly the voltage should go to zero. This is how I imagine ideally my characteristic to be. But it does not remain ideal because of the presence of this internal resistance of the battery. None of the terminals or uh, none of the parameters are actually absolutely resistor, inductor, or capacitor, right? There is always some lead inductances, parasitics, or non-idealities present everywhere. So even in a battery, the lead connectors that you connect the terminals from inside of the electrodes to the battery, they have certain resistance. That is what we call as internal resistance of that battery. Now, that internal resistance of any battery changes with dynamically changes with lot of parameters. And one of the parameters that it dynamically changes is with the C rate of the battery. So in this curve, if you see, the practical characteristic will not be like the black ideal characteristics. It will be somewhat deviated from the ideal characteristics that you can see in the blue curve. So the first is the C by 10 battery, characteristics for the C10 battery. Okay, another is the C5 battery and another is the C.5 battery, that is 2C. So the moment I am increasing my discharge current, my characteristics are becoming more deviated from the ideal characteristics. So that is our thing to remember from here is as as you increase the discharge current, our characteristics deviate from the ideal characteristics. So while discharging, we try to keep. That is why we don't go for fast charging. We never say that fast charging is preferable. We always say that there is an discharge current minimum discharge current at which you should ideally charge or discharge your battery. So fast charging is not good for your battery life. It is just convenient for us. That is why we try to get that battery, but it is not good for or practically suggestible to use that kind of batteries. So now Another parameter after first was capacity, another was C rate, and now the third parameter is battery efficiency. Now, what is battery efficiency? You can see the diagram on the right hand side here. So if we have a solar panel with whatever capacity WHPV, and we have a load with WH load as the whatever capacity, and a battery with WH bat as its whatever capacity, then you can see while charging the battery, electrical energy is getting converted into mechanical energy. So there will be a loss, WHEC, that is electrical to chemical energy conversion loss. And when again the battery is getting discharged into the load, there is another loss that comes into picture, that is chemical to electrical energy conversion loss. Right? So in both, while dumping the energy into the battery and while pumping out the energy from the battery, both the times there are losses involved. So when losses are involved, the efficiency is not 100%, and it is something different. That is why there comes a need to calculate battery efficiency. So efficiency will be whatever delivered to the load by whatever drawn from the source. What I am giving here and what I am getting here and what I am giving here. The difference, the ratio of that is called efficiency. So it can be written in multiple formulas. You can write WH battery as WHPV minus WHEC, or you can write WH load is equals to WH bat minus WHCE. These are all like this. If you remember this diagram, you'll be able to write all in terms of any equations. You just have to remember this efficiencies like notion. What is the basic meaning of efficiency? That's it. This battery efficiency is also called energy efficiency or watt hour efficiency. Now, another parameter is energy or power density. Okay, both energy and power densities can be categorized into two different types. One is gravimetric and another one is volumetric. So, gravimetric is per unit kg and volumetric is per liter. Now, what is the significance of these gravimetric and volumetric? Now, if you think about an electric vehicle, then kg weight, how much kg weight battery is present on the electric vehicle impacts the range of electric vehicle. And if you look at the volumetric parameter, then the liters tells how much space the battery will be requiring. So if you think in those terms, you will be able to understand the significance of the why do we specially have to create a term called gravimetric energy density or power density. And energy density, it's watt hour per something, and power density will be watt per something. So when it's per kg, it's called gravimetric. When it's per liter, it's called volumetric. Similarly, for power density, power is like instantaneous. We all know that P power is the derivative of energy with respect to time, or energy is the integral of power with respect to time. So power, whenever we talk about power, it's the instantaneous requirement. So instantaneous, if I want to accelerate my electric vehicle or I want to apply the brakes, then I will think about gravimetric kind of power density. And when I'm talking of volumetric power density, I'm talking about the size of my vehicle. This is how these energy and power densities play a role, and they play a very important role in our design of electric vehicles, because weight is one of the very important parameters. Either we compromise on the weight of the vehicle or the range of the vehicle. So all these vehicle manufacturers play with these parameters. Now, because of the limitations of the battery chemistry, a pattern is observed between energy density and power density. You could either have energy density or power density. You cannot have both. So there is a trade-off between the two. So you have to find the optimum point where you have optimum value of both energy density and power density. Now, when you talk about various kinds of batteries that are available in the market, there are two extremes. So there is most popularly two used batteries are lead acid batteries and lithium polymer batteries. All of you might have definitely heard of these terms. Lead acid was so far the most popular battery that have been used almost everywhere. Almost all of our houses have inverters. Inverters have these lead acid batteries, dry or wet. And then recently, because of the electric vehicles, you might have heard of the lithium polymer. All the batteries that are present in our gadgets or mobile phones or anywhere, these are all lithium polymer batteries. Now they are both at the extreme of the spectrum. The lead acid batteries have very low initial cost, but they are very bulky and they have poor energy and power densities. So for an application like inverter, I have a lot of space in my home, so I can keep big size lead acid batteries. It's not a problem. So I can reduce the cost and I can keep big batteries for my inverter or UPS system. But when I'm designing an electric vehicle and I want to increase the range of my vehicle, I need to reduce the weight of my vehicle, then I would rather pay more money and make my system compact, right? So that is the both extremes. And this lithium polymer batteries have good energy and power densities. In the curve that sir has shown in his lectures, you have seen that there is a table where they both are at the extremes, and rest of the nickel metal hydride batteries, they are all in the middle. So you just have to remember this like rough pattern of these batteries. That's it. Now, when it comes to next is battery selection. How do you select a battery for any application? So first of all, we start with identifying the chemistry of the battery. Okay, so how do you decide the chemistry of the battery? You based on the applications, based on the availability and the capital investment. So we just discussed about lead acid battery and lithium polymer battery, right? Since the availability of lead acid battery was it was easily available in the market. That is why most of the people initially were using lead acid batteries everywhere. But now you are seeing lithium polymer also, so you could think about using lithium polymer as well. And I will think about my capital investment. If I have less money, I will just use a lead acid battery. If I have more money and I want my system to be compact and lightweight, then I'll go for lithium polymer. So depending on application, availability, capital investment, all these parameters, we finalize what kind of battery chemistry we want to go with. Next thing is allowable depth of discharge for the battery. So all the batteries, when we choose, so all the batteries that we have allowable depth of discharge connected to their chemistries. So depending on what kind of battery we are using, we'll get and the allowable depth of discharge from its manufacture from their manufacturer or its data sheet. Okay, so there are two extremes here also. So there are either deep discharge batteries or there are low discharge batteries. So if I have in my vehicle I have an application of there are separate batteries for starting, lighting, and ignition. So these are the applications that are momentarily used. I don't start my vehicle continuously, right? I just start my vehicle once. I just ignite my vehicle once. So these batteries are just used for few minutes. They are not used continuously. So I could go for a low discharge batteries there, like lead acid batteries here, which have high power densities and are not required continuously. Just a second. Am I audible to all of you still?
Yes, ma'am. Yes, ma'am.
Okay, if you find any problem with the voice, then please let me know. I'll continue. Yeah, so as we were discussing, so we could use low discharge batteries for applications like for applications which require to be turned on for some point of time. But if I want to continuously use a battery, like suppose I want to continuously run my all my home appliances on inverter only, then I will use deep discharge batteries like lithium polymer because I want to draw continuous current from that. So depending on what kind of application and what kind of load profile are you targeting? Are you thinking of getting continuous current from the battery or interrupted current at some interval of time? Depending on that, that will also impact the decision for what kind of battery you are going to use. And that will fix the allowable depth of discharge for your battery. Next thing we'll do is we'll find out the whatever requirement of the load profile, basically load profiling. Basically, if you talk about your home, in your home, how many lights are there, how many fans are there, refrigerator, AC, all these appliances together will give you a rough estimate of what is the watt hour requirement of your load. So that is what we'll estimate next. After that, we'll calculate the capacity of the battery. Now we have already obtained the watt hour load from our load profiling, and we also know the depth of discharge. So using these two parameters, we can obtain the watt hours of my battery. Now, after knowing the watt hours of my battery has ampere hour ratings. So I need to find the ampere hour rating of the battery. That is just we'll divide our watt hour battery rating
with the nominal voltage of my battery. So this will give me the ampere hour rating of my battery. So I have got the first parameter of my battery. I have got the chemistry of my battery. I have got the ampere hour rating of my battery. Now the next thing is C rate of the battery. Now in order to determine the C rate of the battery, we look at the discharge current. What kind of current will be taken from a battery? What is the load that is connected to the battery? So if you talk about this profile, then from point A to B, if that is the region in which discharge current is very low, in that low region you could approximate the characteristics as a linear characteristics. That is, you could just say I into t is constant, and from the part of the curve from A to C, that is the region in which discharge current is of higher magnitude, after crossing the point A towards C, if you look, then the characteristics is no more linear. It's sort of follows this I to the power n t equal to constant, where for simplification n could be treated as a square. So this from in A to B region the equation is I into t equal to constant, and from A to C region the characteristics shifts and it could be more closely approximated as I square t equal to constant. So depending on in what region I am trying to operate in this ID versus T curve, my C rate of the battery will vary. That means what kind of current I'm trying to discharge from the battery, my C rate of the battery will vary. So if you look at the point A, if I am trying to operate at this point A, then for let us assume the discharge current is 5 amperes at this point, and this discharge time is 20 hours. Then this tells me that my battery's capacity is 100 ampere hours, right? But if I try to move from point A to this point, say C, then you will see that say this is 7 amperes current and it is operating for 10 hours now. Now my battery capacity has reduced to 70 ampere hours. So this capacity reduction has happened because we have increased our discharge current. So that is what I was trying to say before, that if you increase the discharge current, your battery capacity will reduce from a C20 battery to a C10 battery. So it will not always be in the same proportion, but it will always be reduced. So therefore, while deciding the C rate of the battery, you have to consider what will be the discharge profile of your battery. Okay. So next, there are rest other energy storage methods apart from just the electrical battery. So electrochemical storage takes battery into account. So battery is the subvertical of electrochemical storage. Then another could be pumped hydro storage. In pumped hydro storage, what we do is we use the energy from solar PV in order to drive the pump. That pump stores the water in an overhead tank. Now, what happens when you store the water in overhead tank? When you raise any object to height h, we increase the potential energy of that object. If m is the mass of that object, then the changed potential energy of that object is m into g into h, right? So we are increasing the potential energy of that object using our solar panel. And now when I want to discharge that energy, what I will do is I will open the valve, water will fall from the high level to lower level and it will rotate the turbine. That turbine will be connected to the shaft of the motor and that motor will start generating. That means now I am converting my the energy that I have stored in my stored water in overhead tank and converting that energy again into electricity. So this is what happens in pumped hydro storage. Then there is another type of storage called compressed air storage. In compressed air storage, using the energy from the solar PV, we give it to the motor. The motor stores the compresses the air and stores it in a constant pressure chamber. And when we want to discharge that energy or when we want to use that energy again, we will just open the valve. That pressure energy will go and rotate the turbine again, air turbine, and it will rotate the shaft of the motor, which will now act as a generator and we'll get electrical energy. So this was another type of storage, or another could be a flywheel storage. So we just we using the on the shaft of the motor, we'll connect a big flywheel, which will continuously rotate based using the input from the solar PV, And once when we want to take that energy back, we will just connect that energy again to the shaft of the generator, and it will give us the electrical energy. So there are many other storage methods possible, but all these rest of the efficiency of almost all these storage methods is around 60 to 70%. So they are almost same that way. But when you look at the implementation, then implementation is the simplest for electrochemical storage. That is why mostly, and it's easily implementable. It's scalable. That is why mostly we go for electrochemical storage. Now, sizing of PV for applications with battery. So just to summarize the steps, what to do in case you have a PV application with battery. So we will first determine the load profile. So in order to determine the load profile, we have divided our day in two parts. One is the day part, another is the night part. So from around 6 a.m. to 6 p.m., we call it the day part. That is the part of the day during which we have sunlight. It from the sunrise to sunset, 6 a.m. to 6 p.m. around, we call it day part, and rest of the remaining part we call it as the night part. So we calculate what hours of the day part, then what hours of the night part, then we calculate the peak load current. What is the peak amount of load current that my load needs? Then next is the average load current during the entire day. These are the four parameters that I need to know, which constitutes my load profile in order to carry on the sizing calculation further. Now, next calculation is of the days of autonomy and recharge. Now, what is the days of what are the days of autonomy and recharge? So, what happens in when you know that there are cloudy days, then there will be no suppose there are no solar generation or no solar insolation is falling. That means I don't have any solar energy. That means my solar PV won't be able to supply any load. So during that time, I don't want my system to stop, or I should not be I should not have insufficient energy to give to my system. I cannot say that I don't have the energy anymore, so I cannot give you electricity. I cannot say to people like that, right? So that therefore I'll have to have a backup designed to be sufficient for those days. Suppose I know that in Bangalore there are 10 days in this particular month or rainy season. During these 10 days, on an average, insolation does not, it gives hardly any generation happens. So I will design a battery backup that is sufficient to give energy during these 10 days. So that is what the days of autonomy tells us. So the days of autonomy are those days during which we, on an average, our solar is not able to generate, and if it's a battery connected system, then we'll have to design our battery considering those days into account. And what is recharge days? So now since you are using battery to give power for so many days, suppose for 10 continuous days I am not having any solar generation, then after those 10 days I will have to recharge my batteries, right? So that recharge days are called as recharge days. So the time during which I don't have any solar energy, that is called days of autonomy, and the time and the days during which I am going to recharge my battery are called as the recharge days. So we have to take these into considerations when we are doing the complete battery system design. Next step, what we'll do is we'll select the battery, and define the battery efficiency. So based on the battery efficiency, if say the number of autonomy days are non-zero, then the watt hour capacity of the battery will be given as watt hour at night, and this will be divided by battery efficiency, because what we are doing is we are storing the energy in the battery, and then in the night we are using it. That means when we are involving battery, that means there will be losses, right? We have just seen chemical to electrical, electrical to chemical, those losses. So in order to take care of those losses, we are dividing this with efficiency of the battery. And if N is the number of days of autonomy, then my battery will have to store for the day and night for these number of days, any number of days, right? So I have to supply, I have to store in the battery for the nights normally every day for the night, and then for the day and night both during the autonomy days. Now, in order to size the PV array completely, what we'll first look at what my array has to supply, what all things my PV array has to supply. So my PV array will be supplying my day load, and then my night load, and then watt hour for the autonomous operation. These are the three things that my PV has to supply. Okay, so what is the day load? Watt hours day. What is the night load? Watt hour night by efficiency of battery. Again, we are putting efficiency of battery here because energy is stored in my battery and then it is retrieved back. Therefore, watt hours will be reduced because of the losses that are happening. And third will be watt hours during the autonomous days divided by NR. So why do we do this is, if suppose my per day autonomous capacity, so this watt hour PV that I am calculating, all the watt hours that I am calculating are for just one day, right? So if I am considering that NR is the number of recharge days, then total number, so I will be recharging my battery capacity of WH auto throughout NR days. So during one day, how much energy do I need is WH auto by NR. So NR is the total number of days. Suppose I have a 100 watt hour autonomous day requirement, and I'm going to recharge it for over a period of 5 days. I'm distributing it over the period of 5 days, and I'll be recharging it. So during each particular day, 20 watt hours of the capacity has to be recharged. So I don't need to design my battery for 100. I will design my battery for 20 because I am spreading it over 5 days. And why do we spread it? Because if I won't spread it, I will try to recharge my battery of 100 watt hour capacity on the same day. My sizing will increase, right? My battery sizing will increase, my PV sizing will increase. So that's not a feasible calculation. That is why for an optimized design, we spread it over the number of days. So this has given us all our first, second, and third parameter: the day load, the night load, and the watt hour for autonomous operation. Okay, and we know that watt hour for autonomous operation can be written as WH day plus WH night divided by the battery into the number of autonomous days. So this is the total capacity of watt hours that I need during the autonomous days, right? That is WH auto. So I'll just put this in the above formula and I'll be able to calculate watt hours of the PV that I need. Now, after obtaining the watt hour PV, next thing I'll obtain is average peak power. We'll just divide it with the equivalent hours that we have, and we'll obtain the average peak power that my system needs. And based on this average peak power, you know the relation of A intrinsic. That is the intrinsic area of the panel that you need. And you know that for practical applications, we need to multiply this by a factor of 1.3 in order to calculate the estate area. So this is how we design our solar PV systems. Okay, so this was all you have seen in your past week. So now let us quickly move on to our next assignment solutions. If you have any doubts, please feel free to ask.
Madam,
Yes, yes, please go ahead.
can I ask question?
Yes, yes, sure, sure.
Yeah, equation has written first equation that watt hour PV is equal to watt hour day plus watt hour night upon NB plus watt hour auto divided by NR. So watt hour auto divided by NR. So from where this NR is coming actually?
Okay, so you are talking about this equation, sir. This
Yes.
equation.
This equation. Yes, yes,
Yes.
yes.
So what is happening here is my array. I will just change the color. So I'm using green color. Okay. So yeah. So my PV array has to supply three types of loads. One is the day load, another one is the night load, and the third is the watt hour for the autonomous operation. Right?
Okay.
I have to supply during the day, during the night, and there are certain days when I won't have any solar energy. So during all those days, my battery will have to give the energy, right?
Okay.
Okay, so these are the three things that my PV will have to supply,
Mm.
or the battery will have to supply. So the day load is written as WH day, night load is written as WH night by efficiency of battery. Okay,
Okay.
and then the third is autonomous operation. For autonomous operation, WH auto is the total energy that I need for any number of days. If I am assuming NA as the number of days for which I will have to go for autonomous operation, and NR as the days during which I will be recharging my battery. So, did you understand the concept of NA and NR?
NR is the number of hours of charging,
No, no,
recharging,
NR is the number of days over which you will recharge. They both are
number of
days.
days
Yes, yes, days.
of recharge.
Yes. So what happens is during suppose in Bangalore, suppose in this particular month, I am saying that for 10 days there will be hardly any sunlight. So the number
Okay.
of days for which I don't have any sunlight is 10 days
Okay.
for
The
Bangalore.
10 days is the NR.
No, this is NA. For 10 days, I don't have the solar energy.
Autonomy. Okay.
Autonomy means battery, the solar panel won't help. Solar panel will be completely inactive, not able to generate because sunlight is only not there. Very
Mm.
cloudy weather. So when solar PV is not able to generate, we call as autonomous operation.
Okay.
That means complete electrical energy has to be supplied by the battery bank.
Battery bank.
So that is called NA. And now, since you are supplying with the battery for 10 days, so now after 10 days, on the 11th day, when my sunlight is coming, I will have to start charging my battery, right?
Okay.
So those numbers, suppose I am going to charge my battery within next 5 days. So this 5 days within which I am planning to charge my battery, this is
Mm.
called as NR.
Mm. Okay.
Okay, so that is why what we are trying to do is so this WHPV that we are calculating is per day, right?
Per day. Per day.
है ना? So if WH auto is the complete energy that I need over all these 10 days, then
Hmm.
for one day I will divide it by NR.
Hmm. Okay.
है ना? Because I'll be recharging over NR days. So
Okay.
for one day,
That
how much energy I need is WH auto the
WH auto divided by NR.
yes, yes.
And WH auto is this.
Yes.
That WH
This
day
formula
plus
you got it,
W
right? This formula you got it, na?
Okay. Okay. Yes. Yes.
Okay. So this is how you, when you look at it this way, then you won't have to remember the formula. You will just be able to write it.
Okay.
Anybody has any other doubts? Okay. So I'll move on to the solution for assignment number 5 then. I hope you guys wanted like a simpler assignment. I think they have reduced the level. I hope you all are happy now. Okay, let us start with the first problem. So in this first problem, the incident energy on a tilted flat plate solar collector, that is HAT, is given as 5 kilowatt hour per meter square per day, and the efficiency of the flat plate solar collector is 16%. Given that the total energy available from the PV arrays, that
Is
is
25 kilowatt.
25 kilowatt hour, calculate the estate area in meter square and peak power of the day in kilowatts based on standard insulation. Okay. Now standard insulation we know that it's 1 kilowatt per meter square, and we also know that efficiency is defined as output by input. Okay. And now so output power is equals to efficiency into input power, and input power is standard insulation into area. Suppose A is the intrinsic area. Let us call it as. Now, what power PV is given to us? Okay, and what hour PV we can obtain by multiplying this into HAT minimum equivalent hours. Okay, so for standard insulation, this will be equivalent to 5 hours, right? If we
Hmm.
consider 1 kilowatt per meter square as standard insulation, then from HAT, H equivalent in hours will be 5 hours.
5 hours.
So this will be efficiency into 1 kilowatt per meter square into A meter square into 5 hours. And we know the value of WHPV, that is 25 kilowatt hour, and efficiency is 0.16. This will give us the A as 31.25 meter square This is our intrinsic area, right? Now we know that the estate area is 1.3 times A intrinsic because we need more area, 30% more area for maintenance, cleaning, installation, etc. So the answer is 40.625 meters square. And they had also asked us to calculate the peak power. So peak power can be quickly written as WHPV by the H equivalent, HET equivalent, that is 5 hours. This is HET equivalent hours. This is 20 watt kilowatt hour by 5 hours, which will give me 5 kilowatts. This is the peak power requirement. So in the next problem, a battery has predetermined charging and discharging level. Among the following scheme, which has probably more life cycle? Now, the moment they talk about life cycle and they are telling us the charging and discharging limit, we know that the depth of discharge is proportional to life cycle. That means our life cycle is proportional to the depth of discharge. So, the depth of discharge is maximum in this one. So, our life will also be maximum in this one. So, in problem 3, a battery has a capacity of 3C and it's equal to 120 ampere hours, where C is the capacity rate. What is the maximum discharging current in amperes allowed to the battery? Following the equation C is equals to I into T. Now, since 3C is equals to 120 ampere hours, the battery capacity can be written as 120 by 3 ampere hours, which is 40 ampere hours. Okay. And now it is given as I into T equal to the capacity C, which is 40 ampere hours. Now,
Madam,
yes,
C5 is equal to ampere hour divided by the जो न्यूमरेटर हम लिखते हैं ना राइट हैंड साइड में that is divided by that na. If it is 3C in that it is multiplied factor na, isn't it?
no, it's not so capacity is 3C, 3 times the capacity. It's not the C rate.
It is not the C rate.
So this 3C that is given in the question, that is not a C rate.
That is
is
not C
capacity.
rate.
They have given 3 times capacity as 120 ampere hours.
Oh, 3C is equal to. Hmm. That is not C rate. I got confused with the C rate with the 3C.
Yeah, see, it's written in a bit complicated way. So actually, they have written like C rate later on, but they had in the starting they had written capacity. But that is what they were trying to say from here
Excuse
is
me, ma'am. Excuse me, ma'am.
yes,
But in the questions, it is also written in the bracket that C rate.
C
yes,
rate,
yes,
capacity C rate. C rate, it is written there.
yes, yes.
Then
It
it,
is confusing, ma'am.
so then it will be 360.
I have done same things and I got the wrong. Actually, mentioned that the capacity rate and the bracket written the C rate. So it's a little
Confusing.
Yes, 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 yes. That I just saw it right now. Okay, so
and
in
we
the
have made
starting,
mistakes.
yes. Sorry?
I have already I have already done same mistake. I have done same mistake. Treated as the C rate. You have you told me that it is not the C rate. It is the capacity rate.
Yeah, because if it will be a C rate, then you'll multiply it with 3 times, right?
Yes, yes, yes.
Yeah, ma'am.
Okay, I'll try to convey it to the people, and they might give marks to all then, because they shouldn't have written it like this. Because initially, even I said just the front part of the capacity, so that is why I divided by that. But yeah,
No, ma'am, but it is already written in the bracket, no?
yes,
C
yes,
rate.
yes, yes.
It
They
is already written that C is C rate. C is C rate, not 3C.
okay, okay,
So
okay.
on that logic, this 40 is right.
No, no. So if it will be C rate and 3 is written on the left hand side, then
No,
we
no,
Then
no. It
multiply
is,
it, right?
ma'am, this does not mean that 3C is the C rate. They have already written that C is capacity rate. Right? So C you have to take as capacity rate, not 3C.
No, but if three,
Right.
okay, if C is the capacity rate, so
C is the capacity rate. It can have a value of 3 into C or 4 into C, whatever. They have already written C as a variable, you can say.
no, but ampere hours unit is also
And
there,
they are
right?
saying they are clearly saying that 3C is the capacity of the battery, not the capacity rate.
But normally
Otherwise, they
C
would
rate,
otherwise they would not have given in bracket.
But if okay, so if C is
normally C
the
rate is
capacity rate, then on the right hand side, if you are writing a number, then you divide by it. If on the left hand side you are writing, if it would have been C3, then it would be C by 3. If they are writing 3C, then
then it
whatever,
will be 3 into C.
yes, the capacity will be multiplied. So that actually it's a bit confusing. Both ways could be
I think
interpreted.
that was the trick behind this, nothing else. Because they have clearly said that it is capacity of the battery. Capacity is 3C, not the C rate. Otherwise, they would have stated that the C rate of the battery is 3C. They have
I,
exclusively told there that C is the capacity rate and not 3C.
it is visible. It is mentioned in the C is the capacity rate, but in the bracket, C rated is written. That's make the confusing.
Yeah,
No,
yeah.
That's
you
the
just you
problem.
just you just you just read the statement before comma that
I have
battery has a
written. I have
capacity of
written
3C,
everything.
right?
I have written
Right.
everything. Whatever
And
I have
after
written everything.
after that
Whatever
after
mentioned in the
that
questions.
no, after comma you read where C is the capacity rate. C is
C is a
capacity rate.
capacity rate. No, 3C is not a capacity rate. And in the bracket, is it mentioned C rated? C rate. In the bracket,
Okay,
it is
okay,
mentioned that
guys.
the C rate.
Okay, okay, sir. Let us keep this question on hold for now. I'll try to consult with few other people also, and depending on what review we get, if this is confusing to more people, then we'll try to award the marks. Otherwise, I'll clarify this question again in the next class. What they were actually trying to tell from this question. Actually, the framing is a bit confusing. Even I agree with that. So, okay, we'll look into this question again. Okay, next time. For now, we'll solve it with the assuming that it's a capacity. And okay, for now we'll solve it because that is the one that is given in the solution as well. So we'll just solve using that. But I'll get back to you on this question again in the next class. Okay. So for this, we wanted to find the maximum current. So the maximum current will be corresponding to the minimum time. And if we assume the minimum time to be 1 hour, then the maximum current could be said as 40 amps. Now on the fourth question, a PV array operates at a standard insolation level for 3.5 hours in a day. That means this is HAT ka hour equivalent is given. It is 3.5 hours with 16% efficiency. It supplies power to an electric. Now there is PV. It is supplying power to an electric motor which drives a pump to store water in the tank installed at a height of 10 meters. Okay, this pump will store the water in a that is placed at a height of 10 meters from the ground. Okay, motor has 88% efficiency and pump has 92% efficiency. Ignore the losses in the branches or paths of energy flow. Following the standard insulation for the given time, what is the expected energy in megajoules stored in the overhead tank? And intrinsic area is given as 25 meters square. Okay, now that we are asked to calculate the energy in megajoules, expected energy in megajoules stored in the overhead tank. Okay, so we know that standard insulation is 1 kilowatt per meter square and intrinsic area is also given. So we'll first start with calculating what is WHPV. So PV output is efficiency of PV into PV input and PV input is standard insulation into intrinsic area. And WHPV, if you want to calculate, then we'll just multiply it with the H equivalent hours. Will give me if you just put the values, then WHPV will come out to be 14 kilowatt hour. Now, this WHPV is given to motor here, which is 88% efficient. So, if I multiply this by 0.88, it will give me the watt hours after passing through the motor. That is given as an input to the pump. So that will come out to be 14 kilowatt hour into 0.88. Now, this is given to the pump, and pump has an efficiency of 92%. So if I multiply it by 0.92 again, it will give me 11.3344 kilowatt hours. So this is the net watt hour that my pump is giving out. So this is the net energy that is going out of my pump, right? Because it's sort of a series circuit, right? PV is giving energy to motor is giving energy to the pump, and then pump is doing the actual work here. So the in order to calculate the expected energy in megajoules stored in the overhead tank, we will multiply it with the efficiencies of these respective series cascaded systems. And since we were asked to calculate in joules, so we know that 1 kilowatt hour is equals to 3600 kilojoules. So using this conversion factor, we can say when we multiply it, then we can say the energy output in megajoules is 40.03 megajoules. Okay. Now, in the fifth part of this question, what is the maximum capacity of overhead tank in kiloliter for the data given in question number 4? And they're telling us to assume 1 liter of water to be equivalent to 1 kg of water. Now, we know that energy in the tank is equals to mgh, where m is the mass, g is the acceleration due to gravity, and h is the height. We know that this energy is 40.803 megajoules, right? Then from that we can calculate mass as 40.803 megajoules by acceleration due to gravity. Let us assume it as 9.8. And height is 10 meters. It was given in the previous question, right? H is equals to 10 meters. So M will come out to be 416.65 into 10 to the power 3 kg, and 1 kg is equals to 1 liter. So therefore, and we want kiloliters. So we can write this at 416.35 kiloliter, right? So in the next problem, the load profile of a small load in a day is shown below. What is the average loads in watt per day? So they have asked us to calculate the average load. In order to simplify this this load profile that is given to us, let us break it down into this one. There are multiple ways in which you can calculate. I am doing it this way. Let me break it into one continuous load of 80 watts throughout the day. Then this is my load number 1. Then rest of my loads are, this is my load number 2, this is my load number 3, and this is my load number 4. So I have broken it into 4 parts in order to calculate the average. Average load in watts will be equal to, so 80 I am considering for 24 hours, so by 24 hours plus, so this number 2, this is load number 1. Now load number 2 is 100 minus 80, that is 20 watts, and that is for 0 to 6 am, that is 6 hours out of 24 hours. Then next is load number 3, which is 150 minus 80, that is 70 into 3 hours by 24 hours. Since it's from 12 noon to 3 pm, it's 3 hours. This is for load number 3. And for load number 4 is 120 minus 80, that is 40. This delta I am taking, okay? These deltas. Because I have already considered the rest of the one big load number 1. 40 into, again it's for 3 hours by 24 hours. So this is for load 4. If you just calculate it, your load while average load will come out to be 98.75 watts. This is the average load in watts. You can calculate it by breaking into different types of parts or individually. But yeah, this is how I did it. So you'll get the same answer any which way you do. So in problem number 7, a battery of 24 volt, the battery is given as 24 volt, has to be sized for fulfilling the load profile shown in question number. The previous question, they are still using the load profile. Calculate the ampere hour required for the battery. Consider the depth of discharge as 80% and energy efficiency of load is 85%. Now, we know that load watts is 98.75 watts in 24 hours. So, watt hour of load will be equal to, we just multiply this watts with the 24, so we'll get it 98.75 into 24. This will give you the watt hours, that is 2370 watt hours. Now efficiency of WH load by WH battery. This will imply WH battery will be equal to WH load by the efficiency, which is 2370 by efficiency, that is 0.85. It will give me 2788.23 watt hours. And using the WH battery, I know that AH battery is equals to WH battery by V nominal of the battery into depth of discharge. 2788.23 watt hours, 24 into 0.8, it will be equal to 145.22 ampere hours. Now, which is the suitable C rate of the battery? Discussed in question number 7. So, in the previous question, they are asking to calculate the C rate. Now, we already know the procedure to find the C rate. Now, in the previous load profile, we know that maximum current drawn by the battery is during 12 pm to 3 pm, which is equal to 150 watts. And input required in the system corresponding to this will be using the efficiency formula. This is the output and we need the input. So input required for this 150 watts will be 176.47 watts. And current corresponding to this power input will be V in by battery. So the current drawn by the battery during this period will be 7.35 amps. So this is like the peak current. Now ampere hour of the battery, we know it's already, we just calculated in the previous question as 145.22 ampere hours. Therefore, from this we can calculate the hours that my battery can stand for with this ampere hour capacity. 145.22 this ampere hours. I just divided with the peak ampere current capacity. It will give me 19.75 hours. Okay, so this is almost like you can take it as 20 hours. So the C rate that is desired and the standard C rate battery that will be available closer to this will be a C20 rate battery. Okay. This was a simple question. Problem number 9. From the given options, which type of battery does not come under secondary cells? So we know that nickel metal hydride, lithium ion, lead acid, all these are secondary. Only zinc, silver oxide does not come in the category of primary cells. Secondary cells. This is a primary cell. And just a secondary. And in the last question, from the given options, which type of battery has lowest energy density?
Lead acid.
We have seen that these are all in the table it was given. We have figures also. Lead acid has the lowest and lithium polymer has the highest energy density. So this was a simple assignment. Okay. Any other doubts regarding that question? I will definitely check up and then we'll discuss in the next class what to do in that question, particular scenario. Apart from that, any other doubts?
Madam, in question number 7,
Yes.
it has not been specified that it is connected to PV. Otherwise, if it was written, then only we should take that night hours and day hours calculation.
They have considered.
Day load, night load. It is not to be considered over here.
No, they haven't given any day note and
They
line.
haven't given.
If they
Okay.
if they would
It is only battery.
It is
Yes.
only battery. Right?
It is only battery, no PV.
Okay.
It is only battery.
Okay, fine. Okay.
Anybody has any other doubts?
Ma'am,
Yes.
DOD and life of a battery both are inversely proportional, na?
DOD and life.
Life of a battery.
So if you discharge the battery to a higher depth, the life will reduce.
But ma'am, actually in the lectures of sir,
Mm-hmm.
we have seen that the DOD and life of a cycle are inversely proportional, and here in question number 2 you have written directly proportional.
No, so here the meaning that we are trying to say is that what we want is the more life for my battery, right? So if I am discharging my battery up to 0%,
It will DOD is higher.
So this, if suppose this is my battery, okay, this is we calculate the depth of discharge from this point, right? So 0% means we are fully discharging the battery. That is obviously bad, right? If I am discharging my battery to 10%, then 20%, then 40%. So this is, I think this is where you are confused. So we calculate from this 100%, right? That is why it's written as directly proportional here. So if we
Lower the
calculate from,
DOD,
sorry.
lower the DOD, higher the life cycle.
Yes. So since in 40% I am just discharging my battery up to this level, that is where my battery will have best life. If I am discharging my battery to 100% to discharging limit up to 0% means my DOD will be 100%. But with respect to this reference, I have written direct proportionality. Okay.
Okay.
So if you change the reference to this limit, this is the full limit, right? And this is the zero limit. So depending on from where you are referencing, you can put your proportionality sign, but the gist will always be same.
Okay, ma'am.
Okay. Any other doubts, guys?
No, thank you, madam.
Okay, guys. So we will wind up for the day. Thank you, guys. Have a nice day.
Thank you.